Welcome everyone to online Precalculus. Today we're going to start section 4.6, the graphs of the other trigonometric functions. And our objectives here are to graph the 4 other functions that we haven't done yet. In the last section we did sine and cosine, and in this section we're going to do tangent, cotangent, secant, and cosecant. We're going to graph them, and we're going to do all the transformations just like we did on sine and cosine on all these other functions. Now, it might seem like this is a lot, but if you understood the concepts of how to transform sine and cosine, we're going to use those same ideas to do all of the other functions, right? There's just a few special things that you're going to have to remember for each one. Okay. So first, let's start with tangent. Okay, so the properties of the tangent function were discussed in section 4.2, and they'll help us to determine what its graph looks like. And because the tangent function is a little bit different than the sinusoidal function, its graph differs significantly. So our sinusoidal functions look kind of like this, right? That was the sine function. And we graphed it by graphing the 5 key points, right? 1, 2, 3, 4, 5. And it had a couple important characteristics that we knew going in. Its domain was one period was, sorry, not domain. Its domain was all real numbers. The period was 2 pi from here to its end. And the range went from 1 to from -1 to +1. The properties of the tangent function are going to be a little bit different, okay? So the period is now pi, because if you remember, the tangent function repeated itself in the first and the third quadrant, right? In the first quadrant, the tangent was positive. Second, it went to negative. Third quadrant, it went back to positive, and then negative, and then positive, and then negative. So it repeated itself every pi instead of every 2 pi. So that means it's only necessary to graph the tangent over an integral of pi, and then it's just repetitions. Okay? The tangent was an odd function, just like the sine is an odd function. Okay? Cosine is even. And so the graph is symmetric with respect to the origin. Here's the important part, is the tangent is undefined at pi over 2. Okay? Because if we remember, pi over 2 is right here. The tangent, by definition, the tangent of theta was y over x. So this y coordinate was, or sorry, the x coordinate was 0 here. So this would be 1 over 0, which is undefined. Okay, so now when we're graphing y is equal to tangent of x, right, when our input is this angle, if the angle is pi over 2, the tangent is going to be undefined. And when functions are undefined, they have some sort of discontinuity in them. And in this case, it's going to be a vertical asymptote. Now, when we graph this, right, it's important to remember what's happening with the tangent of different numbers. So again, here's my circle, right? This point, y over x, the tangent of 0, you should know that is 0. The tangent of pi over 6 was radical 3 over 3, okay, which equals about, I'm going to put this into decimals just to help us look at this, is about 0.6. The tangent of pi over 4 was 1. The tangent of pi over 3 was radical 3, which is about 1.7. Okay, and so now the rest of these are not really angles that we know off the top of our head. So if we use the calculator, if we use the tangent function of a calculator and we plugged in 75 degrees, we would get that the tangent is about 3.7. And if we plugged in 85 degrees, we would get 11.4. If we plugged in 89 degrees, we would get 57.3. And we know that at tangent of pi over 2 is undefined because we just talked about that. But if we plugged in something that's really close to pi over 2, like 3.14 divided by 2 to get 1.57, we would get, if we plug this in the calculator, 1255.8. So if you notice what's happening here, the tangent starts at 0, and then as I go right, this function starts to increase faster and faster and faster. In fact, as I go right, the tangent function goes up a lot, which means as it approaches the asymptote, the graph goes up towards infinity. Okay, so if we start at 0, 0, here is pi over 4, 1, and as we graph this function, the graph goes up towards infinity. Okay, and if we reflect it across the origin, because this function is odd, we get 1 period of my tangent graph. So this is a little bit different than sine and cosine, where we started at 0 and always went in a positive direction. In this case, it is easier to do the tangent graph in the first quadrant and the fourth quadrant, okay? So we're going to get one positive section of the function and one negative section of the function to get one whole cycle, one whole period of this tangent function, okay? Some other characteristics, again, repeated on here, is that the period is pi. The domain is all real numbers except for odd multiples of pi over 2, because at every once a period, the tangent function is going to be undefined. So that's pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, right? Okay. The range is not from 0 to, or from -1 to +1 anymore. The range is from all real numbers, right? And again, just like the domain, there's a vertical asymptote at every odd multiple of pi over 2. At every even multiple of pi over 2, like 0, pi, 2 pi, 3 pi, it has an intercept, and that's this. An x-intercept occurs halfway. This is important. It occurs halfway between each pair of consecutive asymptotes. And we're going to use that idea to help us really graph this. And then here's my other key points. Points on the graph that are 1/4 and 3/4 of the way between consecutive asymptotes have y coordinates of -1 and pi over -1 and +1. So my 5 key points here are not all going to be points anymore. If we look at this first this middle section, right? That's a key part of the function. It's an asymptote. Here's a coordinate that's easy to graph. -pi over 4, -1. Here's a coordinate that's easy to graph. The intercept. So that's 0, 0. Here's a coordinate that's easy to graph. Pi over 4, 1. And then my last key place in this function is the other asymptote. Okay, and then we have 5 key parts of this function that we can use to graph. Technically, they're not all points. 2 of them are asymptotes, right? We're going to start the function with an asymptote. We're going to finish the function with an asymptote. And then, if you notice, what's interesting about this is this point is halfway between these two, just as this point is halfway between these two. And that's a property that we can use to help us graph these functions. Okay, so when we start graphing the tangent curve, that's going to vertically stretch the function. Not really called an amplitude anymore because this function goes up and down to infinity. It's going to be sort of a vertical stretch. This is going to change the period, just like it did before. This is going to be a phase shift, just like it did before. But we're going to approach these things a little bit differently. Okay, and because this function doesn't start and stop with a point. Okay, it starts and stops with an asymptote. Okay, so our technique here for tangent and the next one, cotangent, is we're just going to find these 2 spots on the function. We're going to find the 2 consecutive asymptotes. And all we do for that is we know that this part of the function, wherever it is, has to be in between these two asymptotes. So whatever's inside the function has to be equal to negative pi over 2, and whatever's inside the function has to be equal to pi over 2, because then when you take the tangent of it, it would be undefined. So that means that to find the two consecutive asymptotes, whatever is inside the tangent function, no matter what it says, we set it equal to negative pi over 2 and positive pi over 2, and we get our two asymptotes. Then the x-intercept is halfway between these 2 points, those two vertical asymptotes. The x-intercept is halfway between, and then these 2 points are halfway between that. So we could, if we wanted to, once we find the period, find the quarter period again, because then we're going to get this point, and this point. And that's exactly what we're going to do. So our steps are to find the two consecutive asymptotes, then find the period, the quarter period, and then we start with an asymptote, we go negative A, intercept, positive A. And then if there's a D, if there's a midline, right, we're going to have to add that to all of this, right? This is the middle, so it's not technically the min anymore. It's negative A plus D, and this would be positive A plus D, right? But there's no D in this function, okay? So let's try this out. So let's graph 2 tangent of x over 2, okay? So my first step is, well, first of all, let's list off all the important parts. A is 2. The inside of the function is, so bx minus c is equal to x over 2. Okay, so I don't really care individually. We can list out that, we can say that b is 1/2, c is 0, and d is 0. Okay, but I'm going to use this a little bit different. I'm going to use this information a little bit differently this time. Okay, so to find two consecutive asymptotes, you take exactly what you see inside of the tangent function and you solve it for x twice. The first time you set it equal to negative pi over 2. The second time you set it equal to positive pi over 2. Solve for x. Multiply both sides by 2. So we get that x is equal to negative pi, and we get that x is equal to positive pi. Okay? Now, we could do this next step, find an x-intercept halfway between it, but I think the easier method, rather than doing it this way, find the x-intercept halfway between it and then use 1/4 and 3/4 of the way, let's just find the period. So the period would be, normally, the formula for period of sine and cosine would be 2 pi over b. But that's because the period of sine and cosine started with 2 pi. The period of tangent starts with pi. So the period formula changes a little bit for tangent, and we get pi over b. So my period is going to be pi over 1/2, which gives me 2 pi, which makes 1/4 of the period equal to pi over 2. Okay? So we're just going to skip through these things right here. And actually, let's just get rid of them. Oops. And we're going to use this technique to get our key points. So my first key, let's still call them key points. Okay, the first one is x is equal to negative pi. That is my first vertical asymptote. Okay, the last vertical asymptote is x is equal to positive pi. That's my final vertical asymptote of this function. And in between, I have my 3 other key points. And they're all going to be 1/4 of the period away from each other. So if I add 1/4 of the period, I get negative pi over 2, 0, positive pi over 2. And now we know that these three outputs are going to go negative A, mid, positive A. So I look back at A. What's A? It is 2. So this goes negative 2, 0, positive 2. Okay? To graph this, when I look at this, I start at negative pi. I put an asymptote. At positive pi, I put an asymptote. At negative pi over 2, I have negative 2, 0, and 2. Don't make a line, right? That's not this function, okay? So what we're going to do is we're just going to make, and this is going to be kind of hard, right? We're just going to make a nice smooth curve that flattens out kind of like in the middle a little bit. Again, we're not looking to be super exact. We don't have to do that. We can repeat this as many times, middle, halfway. That's not right. Sorry. Pi, 3 pi is my next asymptote, right? The total period of this function is down 2 pi. So that's the middle of that. This is the middle here. This is the middle here. And we have our next set of coordinates, right? The graph should curve, right? It doesn't look like a line. It does look like a smooth curve in between the asymptotes, a little steeper as you get to the asymptotes, a little flatter in the middle, okay? But again, we're not going to go crazy trying to graph all of these functions, okay? So let's try another one, this time without any of the little help from the steps from the textbook. Again, we're going to go A, B, C is technically a negative pi over 4 because we're shifting the function to the left. It's a positive. We're shifting the function to the left. But it doesn't matter so much, and D is 0. It doesn't matter so much with tangent, okay? Because we're not going to calculate the phase shift the way we did for sine and cosine, okay? Because I don't need to know the point that the function starts at. I just need the asymptote. And so I take whatever is right there. I take x plus pi over 4, and I set it equal to negative pi over 2. And I say x plus pi over 4, and set it equal to positive pi over 2. Okay? And you could actually do this for sine and cosine, right? You would just change these numbers to the place where the function starts, 0, to the place where the function ends, 2 pi. And now you can find the starting point and the ending point and figure out the quarter period and get to the next points as well. So this technique could work for sine and cosine if you wanted to use it there. Okay, so let's subtract pi over 4 from both sides to give me x is equal to negative, that's negative 3 pi over 2, no, 3 pi over 4, 1/2 minus 4th. Yeah, so negative 3 pi over 4 here. Subtract pi over 4, and we get that x is equal to a positive pi over 4. Okay. Period is pi over b, so it's pi, okay? And that makes the, I should have left some room here, that makes the quarter period pi over 4. Okay, so now my key points are x is equal to negative 3 pi over 4. That's an asymptote. First point. Oops. First point. Second point. Third point. Last asymptote is pi over 4. Quarter period. A quarter of the period is pi over 4. So it's negative pi over 2, negative pi over 4, and 0. This is my vertical asymptote, we get negative a, let's just throw this in there, plus d, and positive a plus d. D is 0, right? We didn't do a vertical shift at all, but just don't forget about those, okay? Because those can be a little bit confusing, right? This is the middle, this is the lower key point, this is the upper key point, right? So negative a was 1 in this case. Let's double check. Yep. All right, so this is negative 1, 0, positive 1. To graph, I go back to my graph, which is unfortunately labeled for me, so I have to find negative 3 pi over 4, which is going to be right here. Put a vertical asymptote. Positive pi over 4, put a vertical asymptote. Now there should be a place a quarter of the way through, so that would be negative 1, positive 1, or sorry, negative 1, 0, positive 1, and my graph would look something now a little better. Now we could definitely fill up the graph knowing that the period is pi, 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. Right? We could do this way, and 1, 2, 3, 4. And we could do it to the left as well. With all of these, the pattern is going to be the same. And we're going to get our tangents that keep repeating itself, keep going kind of in this pattern where it's not continuous because I can't draw it all at once, but we get this nice pattern of down to up, then back, jump back down to up, down to up, down to up. So this function is always increasing except for its discontinuities. Okay. Now, so, I mean, we took all the same ideas. We took all the same techniques, A, B, C, and D, period, quarter, period. We rolled the phase shift and the vertical shift into other parts of this function. This is the important part. That's what you have to remember for tangent, is that the two asymptotes happen at negative pi over 2 and positive pi over 2, and that the function increases from left to right. Because the cotangent is going to be a little bit of an opposite. Okay, still has a period of pi. Characteristics are pretty similar. It still has a period of pi. The domain is all real numbers except for integral multiples of the pi. Because remember that the cotangent of theta is now the reciprocal of tangent. So instead of y over x, it's x over y. So here's where y is equal to 0. So that is where the cotangent is undefined. So it's undefined at 0 and pi. So that's slightly different than what we're doing with the tangent function. Okay, so and I think I have a moving picture. I'll show you guys. Go back in a second. So the vertical asymptotes are at integral multiples of pi. The range is still all real numbers. Still, the intercept is halfway between each asymptotes. Still an odd function with origin symmetry. Still quarter periods that we're going to use. But now look, as we go left to right, this function goes down. And I think I had a graphic. No, I didn't have a graphic here. All right. Well, I think I had one at the cotangent. So, oops. Hold on 1 second. Oh, you gotta be kidding me. little technical difficulties. Hold on one second. Hopefully this still is recording. Looks like it is. All right. Okay, so let's try to jump right back into this, and we'll pop to the page that we sort of left off on, which was we were talking about our cotangents. And we can see here was the graphic that I was trying to show you. So as you look at the cotangent, as you spin around the unit circle, right, we are drawing a ratio of how far the the ratio of the x and the y is, and as soon as you hit straight up and down, it is undefined. So kind of cool. Okay, so let's get into cotangent. So the cotangent, let's get rid of this. We can use the characteristics of the cotangent curve, just like we use with the tangent curve, to graph the function. All right, so let's do it. We're going to find two consecutive asymptotes by finding an interval with one period, except here's the difference. The thing you set the inside of the cotangent function to is 0 and pi, as opposed to negative pi over 2 and positive pi over 2. So this function starts at 0 and it finishes at pi with one period if you look at the parent function, right? It starts at 0, goes to pi with one complete period of the function. Okay, so that's our biggest difference here. Everything else is the same. Intercept is halfway, and we'll use the quarter periods to get there. Positive a first, negative a second, right? So this function goes down. So positive a, midpoint, negative a. Okay, so how are we going to do this? We'll simply go a is 3, b is 2, c is 0, d is 0. Amplitude a doesn't really translate into amplitude for cotangent. My period is going to be pi over b. The quarter period is going to be a quarter of that, so pi over 8. C and D I'm not really going to worry about. What I am going to do is I'm going to say that the inside of the cotangent function, I'm going to set it equal to 0, and I'm going to set it equal to pi. So here x is equal to 0, here x is equal to pi over 2. Makes sense, from 0 to pi over 2, the period of the function, one whole period of the function. So what do I do next? Here's my, well, let's write this out. So my key points are that x is equal to 0. That's my vertical asymptote. My first point is pi over 8, positive a. What was a? 3. So that's 3. Then pi over 4, 0. Then 3 pi over 8, negative 3. And finally, x is equal to pi over 2, which is my second vertical asymptote. So this is a, that's the mid, and that's negative a, plus a d if there is any vertical shift. Okay, so then to graph this, yeah. All right, we can figure this out. What do I need? 0, pi over 8. Okay, so, well, let's just do the two asymptotes. So here's 0 and pi over 2 are my two asymptotes. The midpoint is halfway between. So that's pi over 4. Pi over 8 is going to be halfway between those. So we go with 3 and negative 3. Okay. And if you can't guess, it's not a line. That one didn't look too good. This repeats itself every 2 lines here. So I'm not going to do them all. But we get here, here, and negative 3. See if we can do this a little bit better. Yeah. And then, just don't do this, right? Actually try to make it a little bit of a curve. Maybe try to graph this on Desmos and see what it looks like, so that way we can get a better picture. But it's good enough for now. Okay, so for tangent and cotangent, right, what did we have to remember? So for tangent, we had to remember that, right, so for tangent, so y is equal to tangent of x, we remember that the we set we set bx minus c equal to negative pi over 2, and we set bx minus c to positive pi over 2, and then use the quarter period to get the points in between. For y is equal to cotangent x, and then it goes vertical asymptote, negative a, mid, positive a, vertical asymptote. Okay. For cotangent, right, we set bx minus c is equal to 0, and we set bx minus c is equal to pi. Right, we use the quarter period, and it goes vertical asymptote, positive a, mid, negative a, vertical asymptote. So this function is going up from left to right. This function is going down from left to right. Okay. So those are just the things that you kind of have to remember. Quarter period, right? The things that you have to kind of remember to successfully find 5 key points of the function and graph them. Okay. So the last two that we're going to do are secant and cosecant. And we're going to do these a little bit backwards, right? Because of the fact that we should know that cosecant is 1 over the sine and secant is 1 over the cosine. These are reciprocal relationships. So it tells us that the value of the cosecant is always just going to be the reciprocal of the sine. So if I know the graph of the sine, I can just take the reciprocal of that graph. What is a little weird, easy to take a reciprocal of a fraction, a little bit harder to take a reciprocal of a graph. Okay. Well, if we just use the values that x equals across the sine function, it's just going to result in a point that we can plot, except where the sine is equal to 0. When the sine is equal to 0, the cosecant function is not defined. Therefore, it has a vertical asymptote at those points. And it kind of looks a little weird. So what we're gonna do is what I just said before, is that we're gonna obtain the graph of the cosecant by taking the reciprocals of the y values of the sine. Vertical asymptotes of the cosecant occur at the x-intercept, and for secant, we're gonna do the same thing with cosine. Okay, and same thing, that there's going to be a vertical asymptote everywhere the cosine is equal to 0. Here is what the cosecant looks like. Okay, so the sine is the dotted line in red, and you can see that the cosecant shares a couple of key points. So the blue graph is what we want, and one period of the function is one of the looks kind of like a parabola, is the top one and then the bottom one. That is one complete period of the function. So the period is still 2 pi. The domain of a sine function is all real numbers, but a cosecant function is all real numbers except for the places where the sine is equal to 0. So all real numbers except for integral multiples of pi. The range of the sine function went between -1 and +1. The cosecant goes everywhere else. So it's all real numbers that are not between here. So it's from -infinity to -1, union 1 to infinity. Asymptotes, and it is a odd function, same right side up and upside down. Okay, so the secant is cosine, right? Cosine starts at a max, mid, min, mid, max. So it's just going to be shifted a little bit to the left. So still a period of 2 pi. Domain is everything except for places where the cosine is equal to 0. So that is going to be odd multiples of pi over 2. Same range, vertical asymptotes, except this one is even. See how it's reflected across the y-axis? Same on the right side and the left side. Okay, so when we graph variations of this, okay, really what we're just going to do is instead of graphing this 2 cosecant 2x, we're going to graph that. So we're going to graph the dotted line that you see in this picture. Okay? So we're going to graph 2 sine 2x. And if we wanted to graph this function with the secant, we're going to graph the cosine function. Okay? Then we're going to take these functions and turn them into the one that we want by doing these 3 steps. X-intercepts on the sine and the cosine change to vertical asymptotes. Maximums turn to minimums. See, this is a maximum. It is now the minimum of the blue U-shaped thing. And minimums turn to maximums. So if we look at this picture right here's a maximum. It's a minimum. It's a maximum on the sine, minimum on the cosecant. This is a minimum on the sine, but a maximum on the cosecant. Okay? So if this was my picture, if this was the function that I wanted to, if this is the picture of 2 sine 2x, and I wanted to graph 2 cosecant 2x, I very simply say that's an intercept. It turns to an asymptote. That's an intercept. It turns to an asymptote. Asymptote here and here. That's a maximum, and now I make my curve. That's a minimum, and now I make my curve. Goes in between the 2 asymptotes. Don't cross the asymptotes. Don't cross the sine function. It only hits at one spot. And then, we go back this way. Okay? And then I would either erase the blue line or I would make it dotted. So I'd make this dotted because that is not my answer. And in fact, I probably would have started by making it dotted as well. And then the black solid lines would be my actual answer. I don't think I have another one here. Oh yeah, I do. Good. Okay. So again, intercept, intercept, intercept. Changing this to this. Changing sine to cosecant. If this said secant, now you have a problem, right? Now you have to shift the graph, and that's maybe a horrible trick. Asymptote, asymptote. Graph now looks like that. Doesn't cross, right? Okay. Let's try to graph one of these without having the picture to help us. Okay. Same idea here for cosine though. Cosine to secant, same thing. X-intercepts turn to asymptotes. Maxes to mins, mid to maxes. Okay. So here's my function that I want to graph. Okay. I don't want to start there. It's too much of a pain. So here's what I'm going to do. I'm going to graph this. Y is equal to -3. Secant turns to cosine. X over 2. Okay. Now, I should remember how to do this. So A is -3. B is 1/2. C is 0. D is 0. That makes my amplitude 3. And I'm going to have a reflection. Okay, so remember that. Reflection. The period is, we're still going with cosine. So that's 2 pi over b, which gives me 4 pi. So a quarter of the period is pi. Okay. Function starts at the phase shift. The phase shift is 0. So the key points are 1, 2. Let me move this down a little bit. 1, 2, 3, 4, 5. Okay, so my key points are going to be 0, quarter period, pi, 2 pi, 3 pi, 4 pi. Remember the pattern of the cosine. The cosine, right, we're graphing the x coordinate, so it starts at the max. So the max of this function would normally be 3, but we're also reflecting it. So max is turned to min. So this is -3. Middle, maximum, middle, back down. Okay? Normally this would be a max. The negative makes it a min. The middles don't change. Reflections make maxes into mids, maxes to mins, mins to maxes, blah, blah, blah. Okay, so let's graph this with a dotted line. So I'm going to start at 0, -3. That's right there. Then I'm going to go pi 0. So pi 0. 2 pi is going to be a +3. 3 pi 0. 4 pi -3. Let's go to 5 pi. The question said to graph it between -pi and 5 pi. And so this one continues the curve right up there. Okay, so there's my, remember we're graphing here. This is the cosine curve. So I'm going to graph it with a dotted line. Okay, now that I have the underlying dotted function, the intercepts become asymptotes. And let's get a little bit more room here. That's the key point. So my graph looks kind of like that, like this. And again, this is not, it doesn't have, try to make this distance kind of look the same. So don't kind of go like this. All right, that doesn't make a lot of sense. It kind of should have the same general slope until you get close to the asymptote where it goes straight up and down. But this should have kind of like a general same shape as the underlying sine function above it, at least at the start. And there's my function. These 3 black solid lines are my answer to the question which said graph the secant. I used the cosine function as a guide to graph the secant part of the function. Okay. Yeah. Okay. So this again is another secant. Yeah. Okay. So this is another secant. We can change this to, let me just see if there's a cosecant one. Cosecant and secant are really going to be the same idea here, right? One is just going to be with the underlying function of sine, the other is cosine. This one has a d. So let's try this just to make sure we understand this completely. So what we're going to do is we're going to graph cosine again of 2x plus pi over 2 minus 1. Okay, so A is 1, B is 2, C is a negative pi over 2 because we're shifting this function to the left, and then D is -1. I'm probably going to need a little bit more room here, so let's just move this down. Amplitude is just 1. The period is 2 pi over B, so that is pi. Quarter period is pi over 4. Phase shift is negative pi over 2 over 2. So phase shift is going to be negative pi over 4. And D is -1. So the max is 0. The middle is -1. And the minimum is -2. Okay, key points, right? So remember, my cosine starts at the phase shift. So that's negative pi over 4. The next point is a quarter period later, which is 0. Then my next one is pi over 4, and we're going to need a little bit more room. And my next one is pi over 2, and finally 3 pi over 4. The distance from here to here should be pi, and it is. That's good. Okay. Next, the cosine function starts at the max unless it is unless it's reflected. It's not. Then the middle, then the minimum, then the middle, and then back to the max again. So graphing these functions, negative pi over 4 is, okay, halfway in between here, so that's there. What was it? It was 0. Okay, good. 0, negative 1. Okay. Pi over 4, negative 2. Okay. Negative pi over 2, negative 1. All right. Scale on this graph is not great, but that's okay. That is my function. Okay. And then I could keep this going. No. There, there, middle, middle, boom. And I could keep this going all the way across the graph here. Okay, and might as well be complete like this. Now remember what this means. This is my underlying function, not my answer. And now don't forget that this is the middle of the function. That is the midline. So if it helps you, and it looks a little weird here, but if it helps you to draw the midline, you should, because the vertical asymptotes happen not here anymore because we shifted the whole function down. The vertical asymptotes of the secant function happen everywhere that this function crosses the midline. So now we're getting really busy here. I should have maybe used different colors, but too late now. And hopefully you can visualize this a little bit. This was my underlying function. Oh God, this is crazy. Here's my underlying function, boom, boom, boom. All right, so let's graph the real function, the answer in blue. So I go in between the asymptotes. There is the point. Here's my midpoint, so it's going to go like this. This is going to be a very steep function. And we now can graph as many periods as I need to. This is a little extra here, but, you know, always good to play around with some functions that are a little bit harder, a little more challenging. And there we go. So the blue one is my answer. So how did I get it? I graphed the underlying cosine function. I remembered that the midline has been shifted, so it's not where this function crosses the x-axis, or where it's crossing the midline gives me my vertical asymptotes, and the mins and maxes switch, right? This is a max, it turns to a min of the parabola-looking part of the cosecant, or the secant function. Okay? Let's wrap this up here with a picture of the 6 curves that we've done. Sine starts at 0, gives me a nice sinusoidal curve. Domain is all real numbers, range from -1 to +1, period is 2 pi. Cosine starts at a max and gives me a nice sinusoidal function again. Domain all real numbers, only these two. These two are the only one that have domain of all real numbers. range from -1 to +1, period of 2 pi. This is the tangent. It goes up from left to right. It has vertical asymptotes at every odd multiple pi over 2, and the period is pi. That's the cotangent, as you could tell because it's going down. And again, period is pi. Domain is everything except for multiples of pi. Cosecant and secant come from the underlying function of sine and cosine that you can see right there. Okay, so period is still pi, or period is still 2 pi. Domain is everything except for wherever we have the asymptotes. Here they're multiples of pi, here they're multiples of pi over 2. And the range is everywhere where the cosine and the sine are not. So from negative infinity to positive -1, union 1 to infinity for both of them. And I'm not going to do that. So that was 4-6, graphs of other trigonometric functions. Sorry about the little tech hiccup in the middle.